ADCON 0. So back up here, we saw these bits earlier. We're back here at ADCON 0. We saw these bits go done and A to D on. So at this point we're ready to turn the analog to digital module on since we've completed all the other configurations. So A to D on is a typical logic high. So A to D converter module is enabled. We're going to assign the add AD0 or ADO on rather to a 1. So let's do that. So ADCON 0 bits dot AD on is assigned a 1. That's going to be turn A to D converter on. And at this point we're done with our configuration. So we're ready to begin our infinite while loop. Before we do that, let's take a quick aside. So basically, if we had never used the analog to digital conversion features of this chip before, when we went to this section, we would have seen a little bit of verbiage on it, and then the document pretty quickly gets to mentioning the control registers. And then we have these nice tables for each register. Pretty much everything in the 18F4550 is the same idea. For example, let's say we wanted to do USB communication and we had no idea where to start. We could look in the index, find USB, and it's going to have a nice description here and some nice diagrams and stuff. And then almost immediately it's going to get into discussing the different control registers, UCON, UCFG, USTAT, UADDR, etc. And at the end of each section in the datasheet, it's going to have a summary of all the registers that are pertaining to that functionality. So for example, the USB section is particularly long. This is kind of a preview of our third demo board here a little bit. And sure enough, here we see these other similar tables for each register. And eventually, when we get to the end of the USB section, there'll be a list of, and here we are, registers associated with USB module operations. So then at the end of that section of the document, of the datasheet summarizes for us all the registers that we need to be concerned with. And again, all these other functions will be pretty much along the same lines. For example, interrupts, I/O ports we've already taken a quick look at. Of course, the first thing it does is mention the tris register and the port register. Timers would be similar. For example, let's say we wanted to know how to do I2C communication. That happens to be under this section here, Master Synchronous Serial Port Module, which performs both SPI and I2C communication. But let's say it discusses SPI first and then I2C. So if we type I2C, that'll jump us down and do a few searches here, enter a few times. That'll jump us down to I2C mode. So again, once again, it has a bit of a brief description, a nice helpful diagram here, and then it lists all the registers you need to know: SSPCON1, SSPCON2, SSPStat, SSPBuff, SSPSR, and so on. And then it describes the registers in a little bit of detail, and then we get to those same tables that tell us what each individual bit in those registers are and what we need to set them to perform I2C communication. And there's the next register and so on. And again, if we go to the end of that section, hopefully I didn't just skip by it. No, I didn't. The I2C section is also pretty long. More data on timing here. Baud rate generator, that's more I2C data. More I2C timing diagrams. But eventually we'll get to, here we are, a table, registers associated with I2C operation, and then this is all the registers. These PIR, PIE are pertaining to interrupts, and then TRISC and TRISD, of course you have to set your tri-state gates to the correct input and output, and then we have the registers that are specific to I2C communication here. SSPBuff, SSPADD, SSPCON1, SSPCON2, SSPStat, etc. So any of these are going to be the same idea. And in fact, if we look back to the beginning of the document and we look for special function registers, like for example the OSCON register was one of the first registers that we looked at, so let's search for that a few times, and that'll take us down to a table of all the registers if we search from the beginning of the document. And here we are. This section here, special function register map, lists all of the special function registers, and then, for example, in the case of the OSCON, it specifically lists these registers are implemented as static RAM in the data memory space. So it even specifically lists the location in data memory where each register is found. So this is really the magic that makes the hardware-software interface of the 18F4550 work. It's basically the same theme for any of these. You have to look up the applicable registers to what you're doing. Then you have to set the configuration bits to what you need them to be. And then you're going to manipulate certain bits within those registers as an ongoing thing when you're working with that feature. So for example, when we finish our analog to digital conversion section, which we'll get to in just a moment, we're going to need to manipulate the go done bit that we looked at earlier, and that will tell us about the timing and results and so on of our analog to digital conversion. But first, let's set our digital switches. So now we're going to begin our while loop. So while 1, if switch 1 equals 1. So this is going to be if switch 1 is off. And that's logic low. I'll explain that in a moment. That means we're in digital mode. Okay, so let's take a look at our diagram. So if switch 1, if this switch is, as we just stated here, if this switch is off, we'd like to enter digital mode, and if it's on, we'd like to enter analog mode. So if we put an if statement here, if switch equals 1, if you have a software background and not a hardware background, that might seem backwards to you because we're checking if it's 1 to see if it's off. But looking at the circuit, if this switch is open, then there can't be voltage drop across R14. So pin 3 here, RA1, is going to see the full 5 volts. Whereas if this switch is closed, then there will be a voltage drop across R14, and we'll have 5 volts at the top of the resistor but 0 volts at the bottom. So therefore the 0 volts will carry over here to pin RA1, which will see 0 volts. So in other words, we have a logic low situation. If the switch is open, we're going to have 5 volts here. If the switch is closed, we're going to have 0 volts. That's unfortunately that's common in digital electronics. If you have a software background and you're not used to it, you're going to have to kind of get comfortable with that because you're going to see it often. It always helps to comment that in code so you don't get mixed up with logic low versus logic high. And you'll notice also that the other 2 switches are wired the same, so they're also going to be logic low. So now we're going to type if switch 2 is 0. So that's going to be if switch 2 is on, and again 0 is on because it's logic low. Then what we're going to want to do in that case is we're going to want to turn on LEDs 0, 1, 2, and 3. So since we had our nice pound define statements up here, we don't have to type port B bits dot RB3, port B bits dot RB2, etc. We can just type LED 0, LED 1, LED 2, LED 3. So LED 0 is going to be assigned 1, LED 1 is going to be assigned 1, LED 2 is going to be assigned 1, and LED 3 is going to be assigned 1. So let's comment that turn on LEDs 0 through 3. So now if switch 2 is off, we're going to want to leave LEDs 0, 1, 2, and 3 off. So we'll type else if switch 2 equals 1. Let's make our spacing consistent here. Else if switch 2 is off, and again that's logic low. Then we're going to want to turn LED, and I'll just copy and paste here to make this easy. Turn off LED 0 through 3. And after that else statement, now we're going to have if else statement rather, now we're going to have else. And switch 2 should either be on or off. It should never be anything else. So we should never get here. And again, if you're used to a desktop software background, this final else might seem a little odd, but I really suggest putting that in this kind of situation, because although this should never happen, if there's some kind of fault in your circuit or some timing problem happens, you'd be surprised how sometimes you can get into this situation. So for debugging, it's very helpful to leave this here. You could assign a LED to something, and then if you see that LED turn on and you know it never should when you're debugging something, then you know you got into this part of the program. So then we'll end that else. So now basically we're going to do the same thing with switch 3. If switch 3 is on, then we're going to turn on the other 4 LEDs. If it's off, then we're going to leave the other 4 LEDs off. So I'll fast forward this next part since it's essentially the same idea.